Assalamu alaikum. We have obtained the expression for magnetic field at a point along the axial line due to a bar magnet. In this video, we are going to get the expression for magnetic field at a point along the equatorial line due to a bar magnet. For that, I consider this as a bar magnet. We know a bar magnet have two poles, a north pole, another one is a south pole. Every magnet has got two poles. So for that reason, the magnet can be referred as magnetic dipole. So instead of calling it as a bar magnet, it can be referred as magnetic dipole. Here di stands for two. Then this bar magnet have a point O taken at the center. This point O is referred as geometrical center of this bar magnet. Now, I am going to draw an equatorial line. What is this? A line drawn perpendicular to the bar magnet can be referred as equatorial line. So, I draw a line perpendicular to the length of this bar magnet from the midpoint O. This is the equatorial line. Now, before going ahead, let me give the length of this bar magnet. This bar magnet have got the length equal to 2L. If it is so, then the length of the distance between midpoint of the bar magnet and any one of the pole is nothing but L. So here, distance between midpoint and the south pole is L. Similarly, the distance between midpoint and north pole is again taken as L. Clear? Then the equatorial line that I have drawn have length equal to R. Okay. So here I take a point. I take a point here. I name this point as C. This point is taken as C. Then I connect this point C to north and the south pole. Something like this. I do the same thing to this side as well. Okay. Now here point C. At point C, I am going to find out the magnetic field due to this bar magnet. Okay. The line that I have drawn here, which connects the point C to the north and the south pole, have distance equal to R dash. Represent the letter R dash. You can remember this. Now, to get the magnetic field, what I do, I place a unit north pole at point C, whose magnetic pole strength is QMC. The magnetic pole strength of a unit north pole placed at point C is QMC, which is equal to 1 ampere meter. 1 ampere meter. So it means I have placed a unit magnetic north pole at point C. If it is so, we know whenever same poles are brought close to each other, they repel. So this north pole, unit north pole will repel the north pole of the magnet. So there will be a repulsive force exists between north pole and the unit north pole, present point C, which acts away from this line. So this line that I draw actually represents the direction of a repulsive force present between north pole of the magnet and unit north pole present at point C. I name this force as Fn vector. It acts along this line. Okay, similarly, different poles attract. An attractive force exists between different poles, between south and the north pole. So, the force that acts here between unit north pole and the south pole of the magnet is acting towards the south pole of the magnet, represented by this line. Okay, it acts towards the south pole, and this force acts away from the north pole. Now, I represent this force letter Fs vector. Clear? Now, these two forces, force is nothing but a vector quantity. It has got both direction and magnitude. Okay, so if you look at this carefully, this force is inclined at some angle. Okay, this way. Suppose if I have a force which appears something like this. This is the force. Then I can say that the direction of this vector quantity is along x-axis, minus x-axis. So if I have a line, something like this, and I use this one to represent some vector quantity, then I can say that the direction of this vector quantity is acting along the y-axis, positive y-axis. Okay. Here, we have a vector quantity which is inclined at some angle. Okay. See here, it shows the variation along the x-axis and as well along the y-axis. See, it progresses along x-axis and also it shows the variation in the height. That is, it shows variation along the y-axis. So, Fn vector and Fs vector have components along the x-axis and as well y-axis. We call this as components of vector. Okay, this I am going to show you here. Okay, I will take up these two forces separately and I will split them and I will show the rectangular components of these two forces acting at point C. Okay, first I take this repulsive force. That is Fn vector. Okay, I am going to find out the component of Fn vector is shown by this and this line. Okay, this is the vertical component of Fn vector and this one is the horizontal component of Fn vector. Okay, now I draw a line parallel to this, and as well I drop a line parallel to this line. It forms a rectangle. Okay. By doing so, if you look at this carefully, you will find that it has got two right angled triangle. There are two right angled triangle here. So what I do, I get this, I take a sin theta. Okay. This one is angle theta. How do we get that? There is nothing but the angle between the length of the magnet and this line NC. What is a theta? Then this angle will also be theta. Clear? This is what I have taken here. Now, in this right angle triangle, the side is just opposite to the angle theta. It's called as opposite side. This is opposite side. This is adjacent side, and this one, whose value is Fn vector, is the hypotenuse. This is the hypotenuse. Okay. So we have three sides of a right angled triangle. Here, sin theta is obtained by dividing opposite side by hypotenuse. Okay. So my aim is to get the expression for this component, the vertical component. Okay. If I get the value of opposite side, then it will be equal to the vertical component. Okay, so just cross multiply this. You see, the opposite side is obtained if I multiply sin theta with hypotenuse. What is hypotenuse here? Okay, I write it here, hypotenuse with the sin theta. Okay, now this can be done here. Hypotenuse is nothing but Fn vector. Fn vector. Sin theta equal to opposite side. Now this can be written as the opposite side can be written as here. Instead of Fn vector, what do I do? I take it this way, Fn. Then I include the unit vector. Okay, the unit vector is the unit vector which acts along the y-axis is nothing but j cap. Okay, it acts along the positive y-axis, so plus j cap is taken here. That I write here. It is written as such. Along with that, I multiply j cap. It provides me the direction. Okay, this is the value of opposite side. I box this for better understanding. Okay, now the value of this side is nothing but Fn sin theta j cap. If it is the Fn sin theta j cap, then the value of this side, which is just parallel to this line, is nothing but Fn sin theta j cap. Okay, this is the vertical component of Fn vector. Now I am going to find out the horizontal component of Fn vector. For that, see, I use this equation cos theta, which is obtained if you divide adjacent side with the hypotenuse. Okay, now here my aim is to get the value of adjacent side. So I take it this way: adjacent side equals to hypotenuse multiplied with the cos theta. Here hypotenuse is nothing but Fn vector. So cos theta equals to Fn vector multiplied with the cos theta. Okay. And here Fn vector can be written as Fn multiplied with the unit vector. The unit vector which acts along minus x axis is nothing but minus I cap cos theta. So okay, here I have done a small mistake here. There's nothing but what is that? The adjacent side. It's not cos theta, it is the adjacent side. Yeah. The adjacent side is kept as such. In the place of hypotenuse, I have mentioned its value, that is Fn vector, and cos theta is written as such. Then I removed the vector symbol. Then I included the unit vector, which does the work of the direction, provides the direction. Okay, so adjacent side, which is unknown to me, and it is going to provide me the horizontal component, is nothing but this. The side is equal to Fn cos theta multiplied with the I cap, minus I cap. So I am going to write that minus sign here. Fine. I box this as well. For better visibility, I do it. So we got the expression for horizontal component of Fn vector as well. There's nothing but this. I'll write it here. This Fn minus Fn cos theta I cap. Okay, it acts in this direction along minus x axis. Then next, I'm going to get the horizontal and vertical component of Fs vector. So that I show here. Take Fs vector. Okay. Then this line provides the vertical component, and this line provides the perpendicular component of Fs vector. Got it? Now we will draw a line parallel to this, and also from this point I will draw a line parallel to this. Clear? It forms a rectangle. Then this line divides this rectangle into two equal right angled triangle. Got it? Then we have two right angled triangle. Right angle triangle. So using the expression for sin theta and cos theta, one can easily obtain horizontal and vertical component of Fs vector. Let's do that. I'm going to follow the same method here. I take sin theta, which is nothing but opposite side divided by hypotenuse. So in this diagram, Fs vector acts as hypotenuse, and from the diagram, if it is this angle is theta, then this angle will also be theta. Okay, so from here, this angle is a theta. Okay, so this part, this line is the opposite side. No, this side of the right angle triangle. Nothing but opposite side, and this is axis adjacent side. Okay, this one as well, adjacent side. Okay, my aim is to find out the opposite side and adjacent side to get a vertical and horizontal component of Fs vector. Okay, I start with this. Now first I will find out the opposite side, the value of opposite side, which will provide me the vertical component. Clear? That I cross multiply. This. Keep opposite side here. Hypotenuse taken this side, so it will multiply. Hypotenuse will multiply with the sine theta. Will multiply with sine theta. So rearrange it. Opposite side multiplied with the opposite side is equal to, here hypotenuse is Fs vector. Fs vector here. Opposite hypotenuse is the Fs vector. Then sine theta is written here as such. Sine theta. Okay, this is how we obtain the value of opposite side. So opposite is the product of Fs vector and the sine theta. Here the Fs vector can be written as Fs multiplied with the unit vector. What is the unit vector? The unit vector along the y-axis, minus y-axis, minus j cap, the sine theta. Okay, this is opposite side. Okay, this can be written as no. So the value of this line is minus Fs sine theta multiplied with j vector. Okay. Now, if it is the value of this line is this much, then this parallel will also have the same value. So, I write it as F yes sine theta multiplied with j cap. I write a minus in here. Okay, this acts along. This is the vertical component. Then I'll get the horizontal component. Now, before doing so, just box this. Opposite side is equal to minus Fs sine theta j cap. Then to get the horizontal component, use this. Cos theta equals to adjacent side divided by hypotenuse. Right. Here, adjacent side cos theta. What is the adjacent side? Is unknown, so it's kept as such. Hypotenuse is Fs vector. Now I cross multiply to get the value of adjacent side. So what I'll get? Adjacent side equal to Fs vector multiplied with cos theta. Then this adjacent side can be written this way. Fs, the direction is given by the unit vector. What is that? The unit vector along the minus x-axis is minus I cap cos theta. Okay. But this is the adjacent side. Now I write it this way. Adjacent side is equal to minus Fs cos theta multiplied with I cap. Now I box this for better visibility. Fine. Now I'm going to write this one here. Okay. Minus Fs cos theta multiplied with the I cap. Clear? This is the horizontal component of Fs vector. So here we have got the horizontal and vertical component of Fn vector and as well Fs vector. Okay, that is shown here. And then I am going to represent these components in this diagram for our convenience. I use this color. The what? Yeah. Then theta j cap. This is the minus F n, not F n, I'm sorry, there is F S sin theta plus j cap. Okay, so vertical components of Fn vector and Fs vector. Let's say. Similarly here, this is the horizontal component of Fn vector. What is that? Yes, minus Fn cos theta I cap. Then this one represents the horizontal component of Fs vector, and that's nothing but F minus Fs cos theta I cap. Cos theta I cap. Okay. So here, if you look at the diagram carefully, you may find that the vertical components act opposite to each other, so they get cancelled. Whereas horizontal components act in the same direction, so they get added up. Clear? So from this derivation, I can write that Fn vector is equal to the component of these two. What is that? F n vertical component sin theta j cap. Then it is these two are added here, plus with the minus, it becomes minus. Okay, so Fn or increase one step here for better understanding. What I do, increase one step here, write plus, then I add this part minus F n cos theta I cap. Fine. So what do I get? I get this Fn vector is equal to F n sin theta j cap minus F n cos theta I cap. This is the taken as equation number 1. Okay, in a similar way, Fs vector can be obtained if we add the horizontal and vertical component. What is that? Start with the vertical component first. This minus Fs sin theta j cap. Then minus, I add this with this part, horizontal component, minus Fs cos theta I cap. Here I go step by step for better understanding. Clear? So what do I get here? I get this. The next step. Fs vector is equal to minus Fs sin theta j cap. Here minus and plus becomes minus. If you multiply these two, we get minus. Fs cos theta I cap. Okay. I box this. Now it is taken as equation number 2. Equation number 2. Okay. For better visibility, I box this one as well. Clear? So we have got two equations now. One represents the force acting between North Pole and the North Pole present at point C, and it represents the force acting between South Pole of the magnet and the North Pole placed at point C. Clear? This is a repulsive force and this one is an attractive force that I have told you earlier. So let's go ahead. Now what will be the total force acting on the unit North Pole at point C? The total force at point C, the total force, or can be called as net force. The total F can be nothing but the sum of these two, the magnitude of the net force. F1 plus F. Yes, clear. So the total force can be obtained if we add Fn and Fs. Okay, this I am going to do now. Let's do it. It is F vector, Fn vector, and this as Fs vector. Now we know the value of Fn vector and Fs vector. From equation 1 and 2, I am going to substitute them here. You see what I get? See? This. First I will substitute the value of Fn vector from equation number 1. This Fn sin theta multiplied with j cap minus Fn cos theta multiplied with the I cap. Okay, I take this within bracket. Now added with the value of Fs vector. That's nothing but it is going to be equation number 2. Fs sin theta j cap minus Fs cos theta I cap. Okay. Now here this is what we have to. I take this as equation number 3. This is taken as equation number 3. Now what will be the expression of force? Let me write that down here. Here the force Fn is nothing but the force at point C due to unit north pole and the north pole of the magnet can be obtained using Coulomb's law. Okay, the help of Coulomb's law it can be obtained. What does Coulomb's law say? It says that the force of attraction or repulsion between two magnetic poles is directly proportional to product of magnetic pole strength and inversely proportional to the square of distance between them. So from that, this we have learned long ago. I have taken a separate video on this. For more information, you can go through that. So here Fn is equal to mu naught upon 4 pi. This is the proportionality constant. Then at pointer we have QMC. I take that. This unit pole strength. Then it is multiplied with the pole strength of north pole of the magnet, which is nothing but QM. Okay, is divided by the distance between this north pole and the unit north pole at pointer C. What is that? It is nothing but R dash. So I take R dash and I square it. Clear? And I think you remember the QMC is nothing but 1 ampere meter. So in the place of QMC I write 1. So do I obtain this? Fn equals to mu naught divided by 4 pi. Here, the place of QMC I write 1. Then here QM divided by R dash whole square. This can be done as Fn equals to mu naught divided by 4 pi 2m upon R dash whole square. So for your understanding, I write here QMC. Since QMC is equal to 1 ampere meter, so we have obtained this value. Okay, I box this. For better visibility. Similarly, Fs value, the force between south pole and unit north pole at point C, can be obtained using Coulomb's law. Similarly, using Coulomb's law, Fs can be obtained as mu naught upon 4 pi multiplied with QMC QM upon R dash square. Okay. Now, if you follow this method, then the value of Fs will be mu naught upon 4 pi multiplied with QM upon R dash square. Okay. Since QMC equals to 1 ampere meter. Okay, remember this. Now, for better understanding, for better visibility, I am going to box this equation. Now, we obtained the expression for Fn and Fes. So, the amount of Fn and F is obtained here. This I am going to use here in equation 1 and equation number 2. From these two expressions of Fn and Fes, it is clear that the magnitude of Fn is equal to the magnitude of Fs. So, equation 3 can be written as equation 3 can be written as F vector equals to, see, wherever I have Fn, I am going to replace this with Fs. So Fn will be replaced with Fs sin theta j cap minus F, replace Fn and write Fs cos theta I cap. Add it with this part. Here, Fs left as such, Fs sin theta j cap minus Fs cos theta I cap. Okay. Now this is what we get if we replace Fn with Fs in the equation number 3. Now, if you look at this carefully, you may find that here certain terms get cancelled. Now this term and this term have become equal, and this two term has got equal values. See, here I have done a small mistake in the substitution. Here I should have mentioned minus sign. No, that I will do here. No, minus sign from here. Similarly, you should mention minus sign here. So by doing so, what happened? These two terms, which has got same values but acting opposite to each other, get cancelled. This and this get cancelled. Whereas these two terms get added up. So we get a new value for F vector. Okay. Something but minus is taken out, common. Fs cos theta I cap, add with Fs cos theta I cap. So what do I get? I get something like this. F vector equals to minus. So both the terms are same. So when we add them, we get this minus 2 Fs cos theta multiplied with I cap. Okay, this is what we get. Here, the force acting at point C, the force experienced by unit north pole due to the magnet is nothing but magnetic field. We call this force as magnetic field. So what I do, I am going to replace F with a B vector. Okay, F is replaced with a B vector. Okay, and here this is the magnetic field at point C, which is along the equatorial line. So B equatorial and BEQ. It stands the magnetic field at a point along the equatorial line. Clear? So this is nothing but 2 minus 2. Now I am going to substitute the value of Fs from here. What is that? something like this. Mu naught divided by 4 pi. Qm divided by r dash whole square. Okay. Now, for understanding, I write it here. The F vector is taken as B vector along equatorial line. Clear? This is how we have obtained this. Clear? Now, I am going to substitute the value of r dash. Okay. And one thing I have forgot to mention, this part I have not mentioned here, but I am going to write here. So cos theta I cap. Clear? Now, if I know the value of cos theta and r dash by substituting them, the final expression for the magnetic field at point C can be obtained easily. Okay. For that, I take this right angle triangle ONC. Okay, which is nothing but a right angled triangle. I take what's that? O N C. Okay, this is right angle triangle. Here we have angle theta. Now cos theta is equal to adjacent side by hypotenuse. Here in this case, this is the opposite side. Okay, and its value is r. Its value is r, and the value of hypotenuse is nothing but r dash, and the value of OM is nothing but L from the diagram. Got it? Now, what I am going to do, I am going to get the value of r dash and also cos theta value. Right here, cos theta equals to adjacent side is L, hypotenuse is r dash. Clear? Now, to find the value of r dash, I am going to use Pythagoras theorem. Pythagoras theorem is used on this Pythagoras theorem. Pythagoras theorem says that the square of hypotenuse, this r dash is equal to sum of square of remaining sides. Here r square plus L square is what we get. So from this, r dash is equal to the root of r square plus L square. Okay, root of r square plus L square calculated as r square plus L square for half. Okay, what is this? Let me write you. Let me show the term here. If we have a value something like this, if you have root of x, then this can be written as x power half. This is what I have done here. In the place instead of root of this value, I written power half here. Okay. Now, by substituting this one, here we get the cos theta value equals to L upon r square plus L square power half. Okay, this is the value of cos theta. This I am going to substitute here in this equation. So what I'll get, I am going to substitute the value of cos theta and as well the value of r dash square. There is nothing but r square plus L square. Okay. So before doing so, I box this. Box this and name this as equation number 4. Now by substituting R dash and the cos theta values in equation number 4. What I'll get? I get this. You get this? Product field equal to minus mu naught 1/4 pi. I write this 2 along with the QM. 2 QM divided by the place of R dash square. I write this R square plus L square multiplied with the value of cos theta. That's nothing but L upon R square plus L square power half. Now we know when we multiply this two term, it has got power 1 and its power is half. Then the power obtained to be equal to, now we get this will be equal to this one mu naught divided by 4 pi 2 QM divided by R square plus L square power 3 by 2. This is what we obtained. How do we get this? Let me show this to you. Before that, let me mention I cap from here that I forgot to mention. And here I'm going to mention both the L and the I cap. Now I'll show you how we obtained power 3 by 2. You see, if we have a product, something like this, x multiplied with x power half, then here if you have x, it means the power is 1. Can minus x power 1 multiplied with x power half. When we multiply two similar terms with a different powers, then what we do usually, we take it as common, then we add the power 1 plus half. What I'll get? I'll get this x power 3 by 2. So x multiplied with x power half is equal to x power 3 by 2. Similarly, when r square plus L square multiplied with r square plus L square power half is equal to r square plus L square power 3 by 2. This is how we have obtained here this. Okay, the next step what I'll do, I'm going to make certain changes to this equation. So here magnetic field at point C, minus in here mu naught upon 4 pi written as such. Then here we have 2 QM multiplied with L. Now this can be rearranged as QM multiplied with the 2L divided by R square plus L square power 3 by 2. Okay, and here we have I cap, which provides the direction. Here, the product of length of the magnet with any one of the pole strength gives us magnetic dipole moment, represented by letter PM. Okay, so it is written as BEQ vector equals to minus mu naught upon 4 pi. The place of this, I write PM divided by this R square plus L square power 3 by 2. And here we have a I cap. Okay. Here, suppose R is very large compared to L. Then this expression L square, which is the square of half of the length of the magnet, is neglected. So this expression can be written as BEQ vector equals to minus mu naught upon 4 pi PM I cap divided by, in the place of this I write R square or 3 by 2. Here this square and this get cancelled, and what you obtained is this BQ vector equals to minus mu naught upon 4 pi. Here when PM is multiplied with the I cap, we get a PM vector divided by R cube. This is the final expression that gives us the magnetic field at point C due to a bar magnet. Okay, magnetic field at a point along equatorial line due to a bar magnet. Clear? Now, if you compare this with the expression of magnetic field at a point along the axial line, you may find it is half of that value. Clear? And one more thing, this acts just opposite to that of the magnetic field along the equatorial line. What is that equatorial line? So if I draw a line along the length of the magnet, then we call it as equatorial line. The magnetic field at a point along the axial line. This line is called as axial line, and this line is called as equatorial line. The magnetic field at a point along the axial line is always twice of this value, and it acts just opposite to it. There we will not find a minus sign. No. Now, before I conclude, I box this. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your question in the comment section. Thanks for watching.